So for 1, we were talking about exponential functions. So that was going to be some number to the power of a variable, so like 3 to the x, 2 to the x. And logarithmic functions are what will undo exponential functions. The same idea behind multiplication undoing division, addition undoing subtraction, logs undo exponents. All right. One of the big things I tried to make a point of whenever we were going through talking about exponential form is that the number, so if we change all this to something like, this is how we would see an exponential, something like f of x equals 2 to the x. 2 is the base. So if you remember that 2 is the base, going from exponential form to logarithmic form should be easier, because this is going to be y equals log base b of x, or the same thing as f of x equals log base b of x. Well, b stands for base. So if we wanted to change from here, from our f of x equals 2 to the x, instead of f of x, I'm going to actually just pick a number. We'll call it 7 equals 2 to the x. If we want to go from this exponential into a logarithmic form, log base b, so we can base b, base, so this is going to be log base 2. And then I think I also mentioned last week that I tend to think of these not in the proper order. So I think of the base, and then I know the exponent is what the log thing equals. So the log expression. So the exponent in this case is x. So I know my x is going to go over here. So right now I've got x equals log base 2, and then of the only thing left, which will be 7 if we're going again from our exponential to our logarithmic form. So it's kind of how they all relate. My preference is to actually not write them this way. I tend to write them log base 2 of 7 equals x. And my head is thinking 2 to the x power equals 7. And anytime I see a logarithm, I think in that order. So I look at the base, and I think the base to whatever power is on the other side of the equal sign equals the number back over with the log. All right, so I know you did them, but humor me anyway. Going through and changing these from logarithm to exponential. So 4 equals log base 2 of 16, base 2. And I know what's on the other side of the equal sign is my power. So 2 to the 4th power equals 16, because we come back around. And we got a true statement, so we should feel pretty good about it. So for this one, where we can't double check to make sure we have a true statement, it's going to be base what? Yep, base b to what power? Equals 32. Right. And again, just going in a circle, because that's how my mind thinks. You can think straight across if you want to, as long as you get it right. This is just how my head thinks about it. All right, for C, it's going to be base what? Base 6 to what power? Okay, equals 216. Very nice. Is that okay? Did you guys remember that from Wednesday? All right. Okay, so these we're going to go from exponential to log. Again, I still think in a circle. If I know if I'm going from exponential to log, I need a log. So this will be log base what? Base 2. And again, because I think in a circle, I'm thinking 2 and then exactly to the 3rd power, so I'm going to put the 3 over here, equals 8. And this is red, log base 2 of 8 equals 3. And all that's saying is that 2 to the 3rd power equals 8. This was the tricky one. The reason this one was so tricky is because we had to change that radical to an exponent. So this is the same as 64 to what power? Yeah, to the 1/3 power equals 4. Whatever number is in the little crook of that radical, that's going to be the bottom of the fraction in your in your exponent. So if I want to rewrite this in log, I've got log base what? And I'm going to go ahead and do the equals. So equals what? 1/3. And then the only thing left is the 4. So log base 64 of 4 equals 1/3. And you could actually put that in your calculator to double check. You could do log base 64 of 4 by using your log button for the Casios. For the TIs, I will show you how to double check that in a little bit. For C, you guys take a second and go ahead and write it out. See if you can write it out straight across. Make it a little extra fun for yourself. All right, so for C, it's going to be log base what? Of equals, nice. All right, super. Is that okay? All right, so we're going to go through and actually evaluate some of these. We don't need a calculator for any of them. We're going to do the first one. So log base 7 of 49. We're thinking 7 to what power equals 49? Yeah, to the second, so squared. So number 2. So 7 to the second power is 49. Yeah. All right, for B, the log base 3 of 27 equals 3 to what power gives you 27? Third power. 3 times 3 will give you 9, and then 9 times 3 will give you 27. All right, this one's a little bit tricky. So we have log. This will is not going to need. It doesn't need a radical to get the 6 on the bottom. What kind of exponent do you need to get the number to go to the bottom? Some sort of negative. So 6 to the negative what? Yeah, just 6 to the negative 1 is going to give you 1/6. D does use a radical. We can't use a radical as the other side of our equal sign. What do you have to do to 81 to get to 9? Right, we're taking the square root, right? So the square root is the same as what power? Yeah, the 1/2 power. So I'm going to translate this one back over to exponential form. So that's the same as saying 81 to the 1/2 power equals 9. And that 1/2, the denominator of the power, so the denominator of your fraction, or of your exponent, that 2 means square root. So we just have the square root of 81 equals 9. There's technically a little tiny invisible 2 right here, but we don't write that for square root. All right, you guys take a minute and try E through H. All right, for E, the log base 6 of square root of 6, I could also rewrite that as log base 6 of 6 to the 1/2 power. You guys agree? It's equivalent? All right, well, 6 to what power is 6 to the 1/2 power? Six to what power gives you 6 to the 1/2 power? You guys are trying to make this super hard. 6 to something equals 6 to the 1/2 power. Just a half. All right. So you guys can go through and think, well, to get the square root of 6, we're doing the 1/2 power. So you could have gone through the traditional way and gone, all right, so 6 to the 1/2 power gives you the square root of 6. Whenever you have the base, so log base 6 of, whenever you have the base 6 and then of 6, they kind of go away, and whatever's left, that whatever that exponent is, will be your answer. So this is just going to be saying that 6 to the 1/2 power equals 6 to the 1/2 power. That's all it's doing. All right, so for F, log base 3 of 1 over square root of 3. Because there's something in the bottom, what do we know about the answer? We know there's going to be a negative involved. All right, negative. And then how do we get the square root? It's going to be what power? 1/2 power. Because square root and 1/2 power are the same. Like cube root, 1/3 power, fourth root, 1/4 power, so on and so forth. We could have rewritten this if we wanted to. So if we wanted to bring this, well, first thing I would do is probably change the radical to 3. Oh, this is going to be too small. Hang on. So 3 to the 1/2 equals something. And then we can take it up top by making it a negative power. So log base 3 and then of 3 to the negative 1/2 power equals, and that's where we're getting our negative 1/2. Just because it was square root. So it could have, if we have something like, if we had log base 3 of the fourth root of 3, then we could rewrite that as log base 3 of 1 over 3 to the 1/4, well, yeah, 1/4. And then to bring it up top, we're going to have log base 3 of 3 to the negative 1/4 power. So for that one, it's just going to be a negative 1/4. So if you have a fraction power, or if you have a fraction answer, it's because you have a radical. And if you have a negative, it's because you were trying to move something to the bottom. And actually, we'll see if G and H get you. They're supposed to be really easy, but maybe not. So log base 11 of 11 is what? Just 1, right? 11 to the first power is 11. Because technically, log base 11 of 11, there's technically a little 1 up there, right? The invisible 1 exponent that's everywhere. All right, and H is supposed to be easy, but is usually tricky. So log base 6 of 1 is 0. Log base whatever of 1 will be 0. So we could have log base 12 of 1, log base 1/3 of 1, any of those to the 0 power is going to give you 1. We all right on this page? I know, it's thinking. All right, so we're going to talk about common log and natural logs. Common log, you're not going to see the base. If you don't see a base, if it's just written out log with no base, it's going to actually be log base 10. But we use log base 10 so much that we just called it the common log, and we don't write the base 10. So for this first one, if I tell you that's the same thing as log base 10 of 10 to the 8th power, what's our answer? Yeah, just 8. Because we're thinking 10 to what power gives you 10 to the 8th. So what about B? Because that's the same as log base 10 of 10 to the negative 3 equals just a negative 3. Because there's not a cube root here, this is the same thing as 1 over 10 cubed. Since it's not a fraction exponent, the negative drops it below, and if you have a fraction exponent, that's the same as a radical. So this one's a little bit tricky. So we have a log, and we know it's a base 10. I'm gonna quit writing that soon. 1 over 10 to what power gives you 1,000? Count your zeros. How many zeros you got? There you go. So log base 10 of 1 over 10 cubed. Well, if I want to rewrite that as log base 10 of 10, it's going to be to what power? Yeah, negative 3. So the answer for this guy is going to be, yeah, just negative 3. This is the same as that one. You just pick up. Yeah. All right, to have even more fun with you. So this is the same. So log base 10. How do you read this? 1 what? Yeah, 1 1,000th. So 1 1,000th. Does that look familiar? Yeah, it looks just like C, doesn't it? And C was the same thing as B. So our answer is negative 3. All right, now we're going to talk about our natural log. Do you guys remember we vaguely, or well, not vaguely, we actually did talk about E a good bit. It's just a weird number, 2 point, and then it goes on forever. It's the same idea as pi, where it actually is a predefined number. So whenever you see that symbol, which the symbol is E, so now the natural logarithms, and it's written, so a natural logarithm it's log base E. But they're not going to ever write it as log base E. They shorthand it, and they put LN. And I don't know why it's backwards, because we say natural logarithm, and then it's LN. And whenever you're entering this in on your homework, that is a lowercase l. All right, so ln, same thing as natural log or log base E. Log base E of 1 is what? 0. Anything. Whenever you've got the of 1, you know it's going to be 0. So natural log of 1 is 0. The natural log of E is what? E to what power gives you E? Yeah, just 1. So for G, the natural log of e to the 6, e to what power gives you e to the 6? Yeah, just 6. All right, and I'll give you guys 20 seconds and let you do H. All right, so for H, the natural log of 1 over e to the 7th, I can rewrite that as the natural log of e to what power? Negative 7. Right, because it was on the bottom, if you want to get it to the top, just change the sign of the exponent. Well, then it's hopefully easy. So natural log of e to the negative 7 is just going to be negative 7. Okay. So this is the same as log base e of e to the negative 7 equals, and we're trying to figure out what it equals. And if we think about this in a circle, if we take it over to exponential, because again, I don't ever think of logs as logs, I always think of logs as exponentials. So we travel in a circle. So we're going to have e to the x power equals, and then we come back, and it's going to be that e to the negative 7. So you end up, these are both base e. Whenever we're looking here, it's both base e. So if they're both base e, then we know the exponents have to be the same for them to be equal. So if we have e to the negative 7 on the right side, we have to have e to the negative 7 on the left side. So that x has to be that negative 7, right? Is that okay? Okay. All right, the graphing part. I know you guys are excited. Okay, so it's nice enough that it still has a picture of the exponentials. So we have our exponential function here in blue and the logarithmic function here in red. Do you guys remember that if they're inverses, they reflect over the line y equals x? Yeah, okay. Okay, can you guys see that that reflects over? If you were to fold it across the line? Okay. This first one is the graph where our base is bigger than 1. So we still have the same rules where the base has to be greater than 0 and it can't equal 1. And if it's greater than 1, then for exponential, hopefully we remember from Wednesday that it's going to have this nice shape to it. For the logarithmic, it's going to come down like this. So we were, for exponential, tracking that 0.01. If it's the inverse, you're swapping the x and the y. So instead of tracking 0, 1 like we did for the exponential, for logarithmic, we're tracking 1, 0. So this is going to be the one we track over here. And we did have, for the exponential, we had our asymptote at y equals 0. Well, because we're having to swap x's and y's, these are inverses. Now we're going to have an asymptote at x equals 0. So we're really just kind of taking everything that we did do for the exponentials and just swapping x and y. Going right like this. All right, this one looks a little bit stranger over on the right side. So this is if we have a base between 0 and 1. So this if we have a fraction or a decimal between 0 and 1. So we did have our exponential function again here in blue. And it's still the inverse, so it's still swapping our x and y. If you were to take this blue line and reflect it over the line y equals x, you're going to get the red line. Instead of tracking that 0, 1 like we were before, now we're tracking the 0.10. Same is still true with the asymptote. With the exponential function, we had an asymptote at y equals 0. So we got to swap x and y to go from exponential to logarithmic. So now we're going to have a vertical asymptote at x equals 0. Is that okay? You guys seem thrilled. Good. The big things to remember, and then you'll, the things that are the same between both of these is that you're starting by tracking that 0.10 for whenever you're graphing your logarithmic functions, and that you're going to have a vertical asymptote at x equals 0. So if you have a vertical asymptote at x equals 0 and you're tracking the 0.10, you know that it's going to originally start on the right side of the y-axis, or it's going to start where x is positive. Because these are in the form of y equals log base b of x, that x can never be negative. Because if we have a positive number, which the base has to be positive, a positive number to any power is going to give you a positive number. So x always has to be positive. Y can be whatever you want to, so you can take any number, you can take any of our options. So any of our numbers bigger than 0. Raise them to any power, positive or negative. Fractions, irrational numbers, so you could raise it to the square root of 2. And you're still going to get a positive x. So if you're getting a positive x, you're going to be staying on the right side of the y-axis, or over where the x is positive. All right. I'm going to freeze this and let you guys think about what you think this will do. So this x plus 2, that's with the x. This plus 2 is not. And then a negative 2 times this. Try to figure out what you think those are going to do, and I'm going to pull up that website. All right, I'm going to go through and actually use just log x. So I'm using log base 10 instead of log base 2. Same general shape, but much easier for me to put in here. If I wanted to do something a little bit closer than 10, but I didn't want to have to type a base, what could I have used? If I didn't want to type a base, but I wanted to use something closer to 2, natural log. Natural log's base e, which is 2.87 or whatever it goes on. 2 and change, right, so it'd be ln. So we'll go back and look at ln in just a second. This is going to be a little bit slow. So instead of having log of x, we had log of x plus 2. So typically, if something was with the x, which direction did it move it? Yeah, opposite of what it looks like, left or right. So you guys would expect this to shift it over to the, over to the left by 2. And it did exactly what we would have expected. All right, so let's do the 2 plus log x. And typically, if you just add a number, it just goes up. And look at that, does the same thing. So if you're just adding or subtracting a number that's not with the x, it's just going to move the whole thing up or down. All right, before we get to that negative 2 part, so instead of graphing the negative 2 log of x, let's just do negative log of x. If the negative is in front, is it going to flip it left, right, or up, down? All right, so I'm hearing a lot of up, down. If it was with the x, you guys would expect it to flip left, right, because x goes left and right. If it's out in front, you guys are expecting up, down. Look at that, it flipped it up and down. All right, if I added 2, what's that going to do to it? It's going to kind of stretch it a little bit, right? So you're going to stretch or shrink. Will the point right here, 1, 0, change? No. Because what we're doing is, so whenever we plug in that 1, we get that this will be 2, we'll get that this will be 0, and then when we multiply by 2, 2 times 0 is still going to be 0. So this is going to stretch it out a little bit, but it's still going to cross through that point. So it doesn't look a whole lot different. Is that okay? So these transformations are still basically the same once you get the idea of the basic shapes. So once you know what log of x is, or once you know the two different, so log of a number bigger than 1 and log of a number between 0 and 1. Once you get those basic shapes, all the rest of the transformations are the same as what we were doing with the exponentials and as what we were doing with like the quadratic, the absolute value, and the square root. Oh, how do we know which shape it has to begin with? All right, so let me see if let me get in the right spot again. So up here, if your base is between or is bigger than 1, so for us that's going to also include just our common log, because that's log base 10, so 10 is bigger than 1. It's also going to include our natural log, because it's log base e, which is 2 and change. Then it's going to have this general shape, where it snugs up against the x-axis, and as it moves up, crosses that point of 1, 0, and then it's going to quickly start going over to the upper right corner. If you have a base between 0 and 1, that's whenever you're going to actually start snugging against the x-axis, but from up top, so from a positive y. And then come across, you're still going to cross that point 1, 0, and then quickly start going to the bottom right. So if you guys can, if you can remember, if the base is bigger than 1, it's going to have this general shape. And if it's between 1 and 0, it's going to have this general shape. Also, if you remember the exponential, if it has a base bigger than 1, it's going to look like the blue one. If you think about just reflecting that blue one over, you'll get the logarithmic one. Is that okay? Okay. You can also plug in a few points. There's always another fun and easy for me. Well, fun, and once you do it a lot, easier. How about that? All right, so for these, we'll make the comments that this plus 2 moved it left 2. This plus 2 moved it up 2. And that negative flipped it which way? Up, down, or left, right? Yeah. And then that 2 stretched it just a little bit. No, so whenever you guys are going through, I mean, you could get a point just by putting in a couple of practice points. And even though we graphed the log base 10s, if we were going to do a couple of with the log base 2, we could. So we essentially have y equals -2 log base 2 of x. For now, you have a less awesome way of doing it. So we'll pick things that we can solve for. So x, y. If x is, let's see, if we do x is 1. So if x was 1, log base 2 of 1 is what? All right, 0. And then 0 times a -2, yeah, it's still going to be 0. So here, maybe we'll do it this way. I'll write the -2 out here separately. All right, let's do log base 2 of 4. So I picked x as 4. So log base 2 of 4 is what? 2 to what power gives you 4? All right, and then 2 times -2? -4. All right, let's do another. And then I'll let you quit. Log base 2 of, let's do 16. 2 to what power gives you 16? All right, 2 to the 4th power, and then 4 times -2 is going to give you -8. See, look, you're getting it. So we could go through and plot those points if we wanted to. But like I said, you guys will have an easier way of doing those in another section or so. Yes, ma'am. All right, so the domain. The domain, is that your x or your y's? So domains are your x's. So we're thinking about this area here for our domain. What do we know has to be true? The log base anything of. The of part has to be what? Here, this x plus 6 is going to have to be what? If we have, let's hear, log base 2 of x. X has to be positive. So this x plus 6 has to be positive. So we know x plus 6 has to be greater than 0. And then we just solve for x. So we're going to move this little guy over by subtracting 6 on both sides. So we have x is greater than -6. If I want to take this from our from an inequality, I'm going to take a mid-step here and put a number line and then go to interval notation. So if this is your -6, am I going to the left or to the right? To the right, everything bigger than. And is that a parenthesis or a bracket at the -6? Parenthesis, because there's not an or equal. So the parenthesis, -6 and bigger, oops, means that our domain, yep, parenthesis -6, exactly, to infinity. All right, the range. So the range is the y's. Well, I can rewrite this as y equals log base 5 of x plus 6. What powers am I allowed to raise 5 to? Anything, right? You can raise to positives. You can do 5 to a -2. I could do 5 to the -1/2. I could do 5 to the negative square root of 2. I could do all kinds of stuff. So this can be anything, the y can. So that means our range is going to be, yeah, everything. So -infinity to infinity. All right, so all that good fun stuff. I'm going to let you guys try the hard one. You're welcome. Yes, ma'am. Not necessarily. The of part, so log base something of, the of part has to be greater than 0. but your answer, because like this one was greater than -6, so that your answer doesn't necessarily have to have a greater, and it doesn't necessarily have to have a 0 in it. All right, so to find your domain, how do you start? So the 7 minus x is greater than 0. And then we need to solve for x, so I'm going to do first. Yep, subtract 7. So negative x is greater than -7, then what? Yeah, so we're dividing everything by a negative or multiplying everything by a negative. Same idea. And the big trick, exactly, flip that sign over. If you multiply or divide both sides of an inequality by a negative, make sure you flip your sign. So we have x is greater than, sorry, x is less than 7. I flipped it, I just didn't in my head. So we have our number line, I've got a number 7. And which direction am I drawing, left or right? Going to the left. And parenthesis or bracket? Parenthesis. So in interval notation, that's going to be what? Yep. All right, very nice. So there's our domain. And our range is going to be what? Yeah, -infinity to infinity. I went through and was messing with it for a second. I couldn't get the range to change, so I'm going to say that the range will always be -infinity to infinity for the logarithmic functions. At least for us. How about that? All right, I think that's, yes.